They say history is etched in stone, yet some stones seem to whisper mysteries that defy our textbooks. Scattered across ancient civilizations are artifacts that shouldn't exist, at least not without the aid of modern technology. Surfaces carved so flawlessly smooth they reflect light like glass, joints aligned with precision finer than a human hair, and metals exhibiting microscopic patterns rivaling today's high-tech laboratories. It's as though the artisans from thousands of years ago worked at the atomic level. If this is true, it forces us to rethink everything we believe about our past. Perfection is rarely a word associated with handcrafted objects. Even in the age of lasers and computer-guided tools, there are limits to how precise we can be. Every edge bears tiny flaws. Every surface carries the marks of its maker's tool. Yet, across the oldest monuments and relics, there are astonishing exceptions that break these rules. Picture a granite block weighing several tons, quarried with tools from the Bronze Age, yet polished so flat that modern instruments detect deviations smaller than a millimeter over its entire length. Or an ancient gold ornament hammered so precisely that under an electron microscope, its microscopic design looks like it came from advanced atomic layer manufacturing, not from human hands. How could this be? Understanding the scale of this puzzle means recognizing how tough these materials are to shape. Granite, for example, ranks high on the Mohs hardness scale, much harder than the copper or bronze tools supposedly used to carve it. Even iron tools would struggle to create the glass-like finishes found in temples across Egypt, Peru, and India. Yet these surfaces exist. Mainstream archaeology often credits patient labor, simple but ingenious tools, and the use of sand as abrasives. But when engineers, stonemasons, and scientists study these artifacts, many remain unconvinced. Consider the perfectly drilled holes in hard stone at sites like Abu Sir and Giza. Modern machinists who examine these holes find spiral tool marks suggesting drilling speeds and feed rates far beyond what ancient hand tools could achieve. Some holes appear cut through granite in a single uninterrupted motion, without the vibration or uneven wear expected from manual drilling. Then there's metallurgy. Damascus steel, famed for its durability and beauty, was once hailed as medieval craftsmanship's peak. Yet microscopic analysis reveals nanowires and carbon nanotubes embedded in the metal, features we can only reproduce in today's laboratories. These structures appear in blades forged over 1,000 years ago by smiths who had no knowledge of atomic science. Zooming in further, some ancient alloys display grain patterns and impurity distributions so uniform it seems the metal was manipulated at the atomic scale, without signs of repeated melting or hammering. We see evidence of processes far beyond what we can replicate without modern technology. This mystery deepens because these examples aren't isolated anomalies. They appear repeatedly across distant cultures that supposedly had no contact. The megaliths of Pumapunku in Bolivia, the ashlar masonry of Cusco, and the precisely cut sandstone of Saqqara all display engineering hallmarks beyond the accepted capabilities of their time. Some sites reveal not just precision, but also techniques unknown to us. Stone fused as if by extreme heat, surfaces polished without abrasives, joints so tight even modern engineers struggle to replicate them without digital design. Blocks fit together like puzzle pieces without mortar, indicating builders who were not mere artisans but engineers with an advanced understanding of materials, perhaps far beyond what we imagine. If these achievements weren't the lucky exceptions but recurring patterns, we must consider a startling conclusion. Either our ancestors possessed knowledge we don't understand, or someone or something taught them. This opens a door to a past that refuses to fit neatly into history books, a past where human capability may have reached or even surpassed limits we now struggle to comprehend. Next, we'll explore a striking case study, an ancient artifact whose microscopic secrets challenge the very idea of progress. In 1851, deep within South Africa's goldfields, miners in the Transvaal region began uncovering something strange. Though they sought gold, diamonds and platinum, what they found were small, perfectly formed metallic spheres, curiosities that would soon challenge conventional history. Initially, only a few of these spheres were discovered, but soon dozens, then hundreds, began to surface. They ranged in size from large marbles to slightly smaller, and most featured an extraordinary detail: 3 perfectly parallel grooves encircling their equators, resembling the precise lathe marks found on modern machine-made ball bearings. Holding one of these spheres in your hand is to grasp a weight of impossibility. The grooves are far too exact, too uniform, to be the result of natural wear or erosion. Geologists were left utterly perplexed by the discovery of perfectly spherical objects embedded deep within solid rock layers that have been dated to over 2 billion years old. These tiny spheres did not show any signs of natural geological formation such as fracturing, weathering, or deformation. Nor did they exhibit the marks typically associated with natural mineral concretions or nodules, which often form through slow chemical processes. Instead, the spheres bore the unmistakable signs of deliberate manufacturing: smooth surfaces, precise symmetry, and uniform size distributions that suggested an artificial origin. This baffling combination of apparent industrial precision and extreme geological age sent shockwaves through the scientific community. To understand why this discovery is so enigmatic, it is essential to grasp the timeline of life and human activity on Earth. 2 billion years ago, during the Paleo-Proterozoic era, Earth was a very different place. Complex multicellular life had not yet emerged. The planet was dominated by microscopic single-celled organisms such as bacteria and archaea, thriving in oceans and shallow seas. There were no plants, no animals, no humans, nothing capable of shaping or manipulating materials with any form of tool or technology. The oxygenation of the atmosphere was just beginning, a process often referred to as the Great Oxygenation Event, which would eventually set the stage for more complex life forms, but was far from complete at that time.
In stark contrast, the spheres themselves looked as though they had been produced in a modern machine shop or advanced manufacturing facility. Their shapes were consistent with engineered metal or ceramic balls, components widely used in various technologies today, from ball bearings in machinery to precision instruments in aerospace and electronics. The implication that such objects could have been formed 2 billion years ago, well before the emergence of any known civilization, presented a profound challenge to conventional scientific understanding.
The spheres' entombment within the rock layers suggested they had been physically incorporated into the Earth's crust at the time of the rock's formation, or soon thereafter. Given the estimated age of the rock, this implies the spheres have been preserved, undisturbed, for an almost incomprehensible length of time. Typically, geological materials undergo significant transformation over millions of years through processes like erosion, metamorphism, and plate tectonics, yet these spheres remain intact, their precision preserved as if frozen in time. Scientists proposed several hypotheses to explain this anomaly. One possibility was that the spheres were natural geological formations whose exact process of formation is currently unknown or poorly understood. Some minerals can crystallize in highly regular patterns, and certain geochemical reactions may produce shapes resembling manufactured objects. Another hypothesis suggested these might be extraterrestrial in origin, micrometeorites or space debris that fell to Earth and became embedded in the sediment before being lithified into rock. However, both explanations have significant weaknesses. The natural formation hypothesis struggles to account for the high degree of uniformity and smoothness of the spheres, which surpasses what would be expected from random mineral growth. The extraterrestrial theory raises questions about how such objects could survive atmospheric entry and subsequent geological processes without significant alteration. More speculative theories venture into the realm of lost or unknown ancient technologies, or even intervention by non-human intelligence, but these ideas remain outside mainstream scientific consensus due to lack of concrete evidence. Ultimately, these spheres represent a tantalizing mystery at the intersection of geology, archaeology, and materials science. They force us to confront fundamental questions about Earth's history and the origins of technology. Are they the remnants of a natural process not yet understood, a trace of extraterrestrial visitors, or proof of lost civilizations or technologies that predate recorded history? The answers remain elusive, and ongoing research seeks to unravel this extraordinary puzzle buried deep in the rock record, reminding us how much of our planet's ancient past remains hidden and unexplored. Skeptics quickly offered explanations. Many claimed the spheres were natural concretions, mineral formations shaped by geological processes that coincidentally resemble manufactured objects. But there's a major problem with this theory. Natural concretions don't form with such perfect symmetry, nor do they produce evenly spaced parallel grooves. The geometric precision of these spheres rivals what our modern engineers would struggle to replicate without specialized tools. Testing revealed something even stranger. The spheres are composed of a nickel-steel alloy not native to the region, an alloy both extremely pure and remarkably hard, scoring close to hardened steel on the hardness scale. And remember, these spheres supposedly lay undisturbed inside ancient rock for billions of years. If these are man-made, it forces us to face two equally staggering possibilities. First, that humans, or human-like beings, manufactured them so long ago that no trace remains in the fossil record, which would require a complete rewriting of our evolutionary timeline, or second, that they were created by something else entirely. By the late 20th century, these objects, dubbed the Klerksdorp spheres, became a focal point of debate. Museums often refused to display them, labeling them anomalies. Best left unexplained. Scientific journals mostly ignored them. A handful of researchers examined the spheres and grudgingly admitted they lacked a satisfactory explanation. So the spheres remain in a curious limbo, too strange to be dismissed, too controversial to be embraced. But the Klerksdorp spheres are only the beginning. Looking deeper into ancient anomalies, you find similar puzzles worldwide. In Colombia, pre-Columbian gold artifacts resemble modern airplanes, complete with wings and tail fins. In India, 2,000-year-old surgical tools bear a striking resemblance to modern stainless steel instruments. And in Japan, a stone compass rose on a remote island aligns with cardinal directions, with precision suggesting advanced surveying skills. Yet these discoveries are often brushed off as coincidences, misinterpretations, or mere chance. But chance isn't so easy to accept when the same patterns emerge repeatedly across thousands of years and continents. At that point, we must ask, is it really chance, or is it the lingering shadow of forgotten knowledge? In the case of the Klerksdorp spheres, this shadow runs particularly deep. Accepting their artificial nature means accepting something even more profound. They were made not just before recorded history, but before the Earth took its current form. And that changes everything. Shift your thoughts from a small metal sphere, no larger than what fits comfortably in your palm, to a massive block of stone so heavy that even today's cranes would strain under its load. Deep within Egypt's desert plateau, far from the busy eyes of tourists, lies an unfinished marvel, the Aswan obelisk. Had it been completed, it would have been the largest stone ever quarried by human hands, nearly 137 feet long and estimated to weigh around 1,200 tons. To put that in perspective, that's roughly the weight of two fully loaded Boeing 747 airplanes carved out of a single granite block. But the true wonder is not just its immense size. Granite is notoriously difficult to shape, even with modern equipment. Diamond-tipped saws and hydraulic drills demand skill, patience, and exceptional precision. Yet here in the bedrock of Aswan, we observe cuts that are strikingly smooth and consistent, almost machine-like. There are scoop marks so uniform in depth and curvature that engineers compare them to the passes made by powered rotary grinders. Mainstream Egyptologists claim the ancient workers used pounding stones made from diorite, a slightly harder rock, to chip away at the granite. According to this view, laborers stood for hours smashing the granite with handheld pounders until it slowly flaked off. But anyone who's tried breaking granite with a rock knows how painfully slow that process is. Minutes to chip a fragment, days to create any meaningful impression. Yet, at the Aswan quarry, entire channels are cut with sweeping fluid motions, as if a drill bit the size of a person had been carefully guided across the surface. Even more puzzling, these tool marks closely resemble those found at other ancient sites across the globe, places like Pumapunku in Bolivia and the megalithic structures of Baalbek in Lebanon. Different continents, different cultures, yet the same style of deep, parallel tool grooves and impossible precision. This raises a question that Egyptology often avoids. Were the ancient Egyptians inheriting techniques rather than inventing them? Did they once have access to machines or methods now lost to history? Had the Aswan obelisk been finished and transported, a monumental feat in itself, it would stand taller than many modern buildings in Cairo. Yet, no evidence remains of the massive ramps or infrastructure that would be necessary for moving such a colossal object. It's as if the technology vanished overnight. Some researchers propose that a sudden catastrophe, natural or man-made, wiped out an earlier civilization possessing far more advanced knowledge than we credit. This isn't just wild speculation. Egyptian temples feature hieroglyphs depicting what appear to be sophisticated devices: a light bulb in the Temple of Dendera, schematic-like diagrams in Abydos, and astronomical alignments rivaling the accuracy of modern observatories. Meanwhile, the obelisk remains frozen in time, half-carved and abandoned mid-process, as if the workers simply disappeared. It stands under the scorching desert sun like a frozen moment in an ancient documentary we were never meant to witness. Modern attempts to replicate the Aswan quarry's cuts using diorite pounders fail. They leave jagged, inconsistent marks, nothing like the smooth parallel grooves there. This leaves us with two unsettling possibilities. Either our dating of the quarry is off and the marks were made later with advanced tools, or more disturbingly, the marks were made earlier by a lost technology. Either way, the unfinished obelisk isn't just a monument to ambition, it's a monument to a mystery hinting at shared global knowledge long before recorded history began. Leaving Egypt and crossing the Mediterranean, we arrive at another baffling ancient site, one submerged beneath the sea. Here, enormous stone blocks lie perfectly arranged underwater thousands of years ago, their existence challenging the origins of civilization itself. Imagine diving off the coast of Japan, sunlight filtering through crystal-clear water, illuminating a rugged seabed. Suddenly, natural shapes give way to sharp edges, straight lines, terraces and staircases, an entire stone city slumbering beneath the waves. This is Yonaguni, near Japan's Ryukyu Islands. To the casual observer, it might look like a strange rock formation, but divers and researchers who have studied it for decades see something far more extraordinary, a geometric pattern defying natural erosion. Massive platforms rise from the seabed like the stepped foundations of ancient temples. Long, flat walkways stretch out, ending in sheer vertical walls more than 30 feet tall. Staircases with perfectly even rises climb to what appears to be a ceremonial platform, surrounded by rectangular pools and a flat plaza, eerily reminiscent of ancient urban planning. The explanation given by some, that the formations are simply sandstone fractured along natural horizontal and vertical joints and then sculpted by erosion into clean angles, runs into significant problems. These shapes are more than just geometric, they are architectural. Right-angled corners seamlessly connect to terraces with perfect 90-degree turns. Massive stone blocks appear deliberately separated from the bedrock, as if quarried intentionally. Certain corridors align with precise astronomical points, much like the megalithic sites found above sea level. Marine geologist Masaki Kimura, who has dedicated years to studying the submerged site of Yonaguni off Japan, argues that it is at least 10,000 years old. This date places it well before the known dawn of Japanese civilization. If Kimura is correct, Yonaguni predates the Egyptian pyramids by millennia and would have been built during a period when humans were still thought to be small, scattered groups with primitive technology. What deepens the mystery is the context of the last ice age, about 12,000 years ago. At that time, sea levels were over 300 feet lower than today, exposing vast stretches of now submerged seabed as dry, fertile land where early humans could have settled. As the ice melted and oceans rose, entire coastal civilizations may have been swallowed by the sea, leaving only the tallest structures visible, like ghostly relics of a forgotten past. This theory of drowned civilizations is not unique to Yonaguni. Similar underwater ruins have been found in the Gulf of Cambay, India, where sonar scans reveal rectangular formations and stone blocks beneath the Mediterranean. Submerged structures off Malta eerily resemble the island's ancient megalithic temples, lying some 60 feet underwater. Off Cuba's western coast, sonar mapping has discovered symmetrical stone formations half a mile below the surface, in an area that would have been dry land over 10,000 years ago. If Yonaguni is indeed artificial, it may be part of a global pattern. Such evidence suggests that large-scale stone architecture existed long before the traditionally accepted rise of civilization in Mesopotamia. This would require rewriting not just a chapter but the very opening pages of human history. Skeptics argue that this is all a product of pareidolia, our brain's tendency to see meaningful patterns in random shapes. They point to other coastal rock formations with straight edges or step-like features formed naturally by erosion, currents, and the brittle nature of sandstone. According to them, Yonaguni's appearance could be an extraordinary coincidence created by natural forces over thousands of years. But nature's uncanny ability to mimic human design down to the finest details is troubling. For example, at Yonaguni, there is a large upright stone slab resembling a standing monolith, deliberately positioned to face a specific direction, almost like a marker for an entrance. Another area contains parallel grooves, evenly spaced, suggesting intentional carving. The more closely you examine the site, the harder it becomes to dismiss these anomalies. Some steps are too uniform to be random products of erosion, and many platform heights correspond to sacred architectural ratios linked to astronomy or mathematics. This is far from what we expect from fractured rock. Nearby on dry land, the Yonaguni stone tablet bears petroglyphs that some researchers believe connect the submerged site to ancient cultures of the region. If this underwater city once stood above sea level, its builders might be the same people who created those carvings, a direct cultural link spanning thousands of years. The question of timing is as provocative as the how. If Yonaguni sank due to post-Ice Age sea level rise, its construction predates all officially recognized civilizations by thousands of years. This pushes the origins of complex architecture and perhaps organized society deep into prehistory. If Yonaguni was part of a wider network of coastal settlements, rising seas may have erased an entire chapter of human history. Whole cities, trade routes, and cultural advancements could lie hidden on continental shelves worldwide, waiting for deep-sea exploration to uncover them. This isn't just speculative archaeology, it's a stark reminder of civilization's fragility. One climatic shift, one geological event, and entire cultures can vanish without a trace. If it happened once, it could happen again. Thus, Yonaguni remains a puzzle carved in stone beneath the waves. Was it the work of an ancient civilization whose knowledge has been swallowed by the ocean, or simply a remarkable geological coincidence? The sea guards its secrets jealously, slowly eroding the site, softening edges, and erasing clues. Time is running out to uncover the truth before it fades completely. But Yonaguni isn't alone. If we travel west across the vast Pacific to the Andes, we encounter another enigma. Perched high on Bolivia's plains lies a site where stones fit together so perfectly that not even a razor blade can slip between them. And some of those stones are so massive that even today's cranes would struggle to move them. As we delve further into this enigma, it increasingly feels like fragments of a vast puzzle scattered across continents, and we're only just beginning to piece together its borders. Picture holding a blade that, when examined under an electron microscope, reveals an intricately arranged lattice of alternating iron and carbon layers. These layers are aligned at the nanometer scale with such precision that even today's most advanced metallurgists would find replicating it without sophisticated laboratory equipment extremely challenging. Yet this blade is not a product of modern technology. It is an artifact from the Middle Ages, known famously as Damascus steel. Its reputation borders on legend. Warriors spoke of swords that could effortlessly slice through inferior blades and armor while retaining a razor-sharp edge after countless battles.
The secret to such exceptional strength was not just brute forging power, but something far subtler: the blade's microstructure. Embedded within these ancient weapons are carbon nanotubes and tiny nanowires, structures that in modern times require carefully controlled laboratory conditions to create. Remarkably, these features were somehow produced by smiths who had no concept of electrons, atoms, or crystallography. Attempts to recreate Damascus steel in the lab have met with some success, crafting materials that mimic its patterns and strength, but the precise formula remains elusive.
These medieval blacksmiths did not rely on written formulas. Instead, they operated by instinct, tradition, and an almost spiritual bond with their materials. They watched subtle color shifts in the metal, listened to the ringing sounds of their hammer blows, and smelled the burning charcoal, all sensory clues that unknowingly guided atomic-level transformations. The forging process demanded extraordinary precision. The temperature had to be kept within a narrow band. Too hot, and the delicate carbon structures would be destroyed. Too cold, and the metal's molecules would not fuse properly. Variables like the air composition, the charcoal's purity, and the cooling intervals after hammer strikes all influence the atomic arrangement within the steel. Modern science only now begins to appreciate the marvel of this craftsmanship. But Damascus steel is just one thread woven into a far older and richer global tapestry. Across the ocean in pre-Columbian South America, metallurgists of Colombia's Muisca culture mastered the art of tumbaga, an alloy of gold and copper, exhibiting a level of control that defies the rudimentary reputation often ascribed to ancient metallurgy. Through a technique called depletion gilding, they manipulated the metal surface, leaching copper from the outer layers to create a brilliant, pure gold finish. Under magnification, this process reveals an almost flawless transition between the atomic layers of gold and copper, so seamless it borders on imperceptibility. It might be tempting to dismiss such achievements as accidental, isolated discoveries by ancient peoples without understanding the science behind them, but such assumptions flatter modern egos more than they explain reality. If these advances were mere chance, why do we observe the same pursuit of near-perfect tolerances replicated over thousands of years and across continents? Why does this obsessive precision appear in Japan's samurai swords, India's Wootz steel, the delicate gold filigree of the Etruscans, and the precisely interlocking stonework of the Andes? Take, for instance, the Inca walls at Sacsayhuaman. These enormous blocks, some weighing over 100 tons, fit together with such flawless accuracy that not even a razor blade can slip between them. No mortar holds them in place. Instead, the stones interlock in complex shapes, like a three-dimensional jigsaw puzzle. This implies the builders did not simply shape one stone at a time, but planned and executed entire multi-block assemblies with tolerances measured in millimeters or less. Even today, with steel tools and digital modeling software, replicating this feat would pose a formidable challenge. Yet the Incas achieved it using bronze or stone tools, and many of these stones show no visible chisel marks. How was such exceptional smoothness possible? Some scholars speculate the use of repeated abrasion with harder stones. Others suggest plant-based acidic compounds that could chemically soften the rock. However, no theory fully accounts for the speed, scale, and uniformity of their work. This is where the notion of atomic-level understanding becomes more than metaphorical. Even without knowledge of atoms or molecules, these ancient artisans might have intuitively grasped how materials behave differently when manipulated at their smallest scales. Through centuries of trial, error, and cultural refinement, they perfected methods that altered microstructures, controlled grain boundaries, and directed molecular alignment. Remember, many revolutionary inventions in human history preceded their scientific explanation. The steam engine came before thermodynamics, vaccination before germ theory, and lenses were crafted long before the physics of light was understood. Mastery can come long before theory. There is also an often overlooked dimension here: intention. Today, speed and profit often trump perfection. But ancient craftsmen frequently devoted months or even years to a single creation. Their goal was not merely function or beauty, but transcendence. Each artifact was an offering, a symbol, a legacy. This philosophy changes the stakes entirely. If you believe your work will endure for centuries or hold spiritual meaning, then aligning a surface within a hair's breadth is no luxury. It becomes a necessity. In many ways, these artisans were closer to the quantum scale than we might imagine, not in scientific understanding, but in relationship. They engaged raw materials directly, forging a bond between human will and nature's forms. The rhythmic hammer strikes, the scent of stone dust and charcoal, the tactile feedback of metal under pressure, all these sensory cues were their laboratory tools. When you hold one of their creations, a Damascus blade, a gilded pendant, or an impeccably fitted stone wall, you hold not just an object, but a frozen moment where human intention met the fundamental laws of physics at a scale invisible to the naked eye. The atoms remain locked in that precise arrangement, set centuries ago by hands that never knew they were shaping matter at the atomic level. Now we will leave the forge and the quarry and enter the domain of measurement itself. To craft with atomic precision, you must first know how to measure it, and here lies yet another profound mystery. The ancient world's astonishing ability to detect and reproduce exact dimensions without digital calipers, lasers, or atomic clocks. At first glance, the fragment appears ordinary, just a weathered relic of an ancient weapon. But when magnified thousands of times, its story transforms beneath the microscope's gaze. Structures emerge, unimaginably small and exquisitely arranged, defying everything we believe about metallurgy before the industrial age. It is at this nanoscale that history whispers a radically different truth. Someone long ago mastered the architecture of atoms.
One of the most renowned examples is Damascus steel. This legendary metal-forged swords, famed for their ability to cut silk mid-air or slice effortlessly through rival blades. For centuries, the secrets behind its remarkable strength and flexibility were lost, buried in myth and legend. Yet in the 20th century, metallurgists examining authentic Damascus blades uncovered something astonishing. Embedded within the steel were carbon nanotubes, microscopic cylindrical structures of carbon atoms arranged with a precision that modern nanotechnology has only recently rediscovered. These nanotubes, together with distinctive patterns of iron carbide called cementite, endowed the blades with their extraordinary properties. Here lies the puzzle. The formation of carbon nanotubes demands very specific thermal conditions that ancient blacksmiths could not have understood. Theoretically, they had no electron microscopes, no awareness of molecular lattices, and no concept of atoms. And yet, they had perfected a forging process that produced effects comparable to some of today's most advanced materials science. Was this the result of pure trial and error passed down through generations, or does it hint at something deeper, an inheritance of knowledge from a forgotten chapter in human history?
Damascus steel is not an isolated marvel. Consider Wootz steel from ancient India, the very foundation of Damascus. Produced in crucibles and traded widely by 300 BCE, Wootz was celebrated for its seemingly magical resilience. The internal microstructures of these ingots exhibit patterns that modern metallurgists recognize as self-assembled at a microscopic level. Once again, a combination of artisanal intuition and concealed science created a material with properties that rival or surpass many modern steels. Even older mysteries exist, like meteoric iron, metal forged not from Earth's crust, but from the cosmic remnants of ancient asteroids. The Tutankhamun dagger, analyzed in 2016, was crafted from such extraterrestrial iron, alloyed with nickel and cobalt in proportions earthly ores cannot match. This was no simple melting and casting. Its flawless, corrosion-resistant finish points to a sophisticated understanding of alloying and polishing techniques, far beyond what archaeologists have traditionally credited to the Egyptian Bronze Age. The deeper we delve, the stranger it becomes. Roman concrete, for example, is famed for its longevity, yet its microscopic chemistry remains underappreciated. While modern concrete deteriorates within decades, Roman harbor walls have withstood seawater erosion for over 2 millennia. Studies reveal that the lime in Roman concrete was intentionally mixed in a way that produced particles continuing to react with seawater, healing cracks and strengthening the structure over time. This is a form of self-healing material, a concept only now emerging in modern synthetic polymers and smart composites. Across all these cases, what we observe is not mere skilled craftsmanship, but mastery at the very edge of atomic behavior, the same realm that governs nanotechnology, quantum mechanics, and today's materials science. This realization compels us to confront a profound question. If these remarkable techniques were attained through empirical wisdom alone, why were they lost for centuries? Why didn't the Industrial Revolution occur as early as 500 BCE, when the essential building blocks of advanced metallurgy were seemingly already in human hands? Some historians argue these achievements were fortunate accidents, products of countless cycles of trial and error, with knowledge preserved only through oral traditions. Yet the remarkable consistency across time and geography in India's Wootz steel, the legendary Damascus blades, and Rome's enduring sea walls suggests something far more deliberate and systematic in metallurgical practice. Even slight deviations in the crafting process can lead to catastrophic failure. To reproduce such feats repeatedly across centuries and continents without the aid of modern instruments implies either a near supernatural level of inherited skill or a body of written and carefully guarded knowledge far more precise than what has survived to the present day. This is where the door to speculation slowly creaks open. Could these be traces of a far older scientific understanding, one that spoke the language of atoms long before Dalton formally described the concept in 1803. If so, what happened to that knowledge? Was it lost in the fires of war, swallowed by societal collapse, or deliberately concealed? The most unsettling possibility is that we have yet to fully recognize the scope of these accomplishments because we have not looked closely enough. For every Damascus sword examined under a microscope, there may be hundreds more artifacts lying forgotten in museums or buried beneath the earth, whose secrets remain invisible to the naked eye. The paradox is difficult to ignore. Modern science prides itself on an ever-clearer vision of reality, yet here are ancient works that suggest we are merely rediscovering truths that others long ago glimpsed. If they truly mastered atomic-level craftsmanship, what else might they have known? In the upcoming sections, we will move beyond the forge and into the quarries, where stone, arguably the most inert and unyielding material, bears evidence of shaping and finishing techniques that, at microscopic resolution, rival the smoothness of machined metal. The mystery deepens here, for stone is not only a harder medium, but a silent witness to technologies that leave no tool marks, no chisel strokes, and defy easy explanation. If metals could speak, perhaps they would tell us that we were not the first to master the smallest scales. Rather, we were simply the last to forget. The deeper we delve into the physical remains of ancient civilizations, the more the lines between history and science fiction begin to blur. In the last chapter, we stood in awe at the sheer impossibility of the spheres, granite sarcophagi, and megalithic marvels such as Puma Punku. But now we must look beyond the stones themselves to the underlying sciences that may have made such precision possible. Because there is a chance, however small, that we are staring at the fingerprints of forgotten sciences operating on scales most people alive today rarely contemplate, the atomic scale. Imagine for a moment a workshop in 2500 BCE, where instead of bronze chisels and pounding mallets, craftsmen wield tools that somehow manipulate matter with exactness down to the thickness of a human hair, or even smaller. This isn't just about accuracy, it's about control. Control over how atoms arrange themselves, how crystal lattices grow, and how metallic grains align for maximum strength. We assume such mastery belongs only in the realm of clean rooms, electron microscopes, and nanofabrication facilities. Yet some ancient artifacts behave as if they were shaped by techniques that would not be invented for another 4,000 years. Take the fabled Damascus steel. At first glance, it appears merely a form of sword-making renowned for its beauty and strength. But studies using modern electron microscopes have revealed something startling. Embedded within the steel's structure are carbon nanotubes, microscopic cylinders of carbon atoms arranged with mathematical precision. In the 21st century, we use these structures in experimental materials to achieve incredible strength-to-weight ratios. Yet, here they are, locked inside swords forged long before the Industrial Revolution. Were these nanotubes accidental byproducts of an artisan's intuition, or did ancient smiths, through generations of experimentation, discover ways to manipulate materials on a microscopic level without ever knowing the word nanotechnology? Then there is the Lydian coinage from around 600 BCE, among the earliest coins in history. Analyses reveal a purity and consistency in the gold-silver alloy difficult to achieve without a deep understanding of metallurgy. Modern metallurgists note that the uniform distribution of metals hints at carefully controlled heating and cooling cycles designed to prevent segregation at the microstructural level, a principle central to today's high-tech manufacturing laboratories. When we manipulate matter with atomic precision today, we rely heavily on machines to perform the work. Computer-controlled lathes cutting to micron tolerances, focused ion beams, etching patterns thinner than a strand of DNA. But an ancient mason cutting basalt with uncanny smoothness had none of these tools, at least none that we have discovered so far. Yet the results, when measured, sometimes fall within tolerances comparable to our most advanced tooling. One controversial hypothesis proposes that some ancient civilizations may have exploited properties of sound, vibration, and heat to affect matter in ways that modern science still does not fully understand. This is not mere speculation. Modern science confirms that ultrasound can induce microscopic cavitation in liquids, certain frequencies can align crystal grains, and thermal cycling can create uniform molecular arrangements. Could it be that ancient workshops were filled with instruments that, while appearing primitive to our modern eyes, produced subtle and profound effects on the materials they shaped? There is also the intriguing question of lost recipes. Formulas so finely tuned and effective that once forgotten, they have proven nearly impossible to replicate. Roman concrete stands as a prime example. Structures built from it have endured 2 millennia of weathering, storms, and relentless exposure to seawater. Its extraordinary durability arises from a self-healing property at the microscopic level, where lime crystals slowly grow over time, sealing cracks and strengthening the material. Modern engineers have only recently reverse-engineered this process, confirming that ancient builders created materials with behaviors that science has only begun to explain in the last century. And then there are the anomalies that defy any neat or simple explanation. Microscopic gold spheres embedded in quartz from South Africa, if the geological context is accurate, date back billions of years, long before humans ever walked the Earth. The Baghdad Battery, a clay jar containing components capable of producing a small electrical charge. The precisely drilled holes in Egyptian stone that suggest a tool feed rate and applied pressure inconsistent with hand-powered methods. None of these phenomena alone can prove the existence of atomic-scale craftsmanship, but when considered collectively, they paint a stranger, broader picture. If such advanced techniques did exist, why were they lost? Perhaps because even then they were not widely understood. It is one thing for a small group of master artisans to guard a process as a sacred secret. It is quite another for that knowledge to survive the collapse of an entire civilization. Technologies, especially those that depend on delicate, repeatable procedures, can vanish almost overnight if the chain of apprenticeship is broken. A sudden war, a devastating plague, the death of key masters, and the craft becomes legend. Yet some of these techniques appear so far beyond their time that calling them legend feels insufficient. When modern scientists discover nanostructures embedded within an ancient blade, they immediately recognize the physics at play, but remain unsure whether they are witnessing a fortuitous accident or a deliberate, extraordinary feat. And if the latter, how much more might have been possible in those lost workshops? Could there have been ancient counterparts to today's semiconductor fabrication plants? Not housed in sterile, clean rooms, but instead located in stone halls with techniques and tools we have yet to decode fully? We also must entertain the uncomfortable possibility that our conventional timeline of technological development is flawed or at least incomplete. If civilizations capable of working with such precision existed far earlier than currently believed, then their achievements might lie buried deep beneath layers of earth and history, their tools reduced to dust, leaving only the toughest artifacts behind, the stones, the metals, the fragments that force us to reverse engineer their genius with only the faintest clues in hand. Standing in a museum today, you might gaze upon a polished obsidian mirror from Mesoamerica or a flawlessly cut crystal lens from ancient Egypt, and feel the faintest echo of this mystery reverberate through time. The knowledge is gone, but the proof remains locked in the perfection of these works. And within that perfection lies a challenge, perhaps even an invitation, to rediscover not just the how, but the why behind these remarkable feats. Because if ancient engineers could shape matter with such mastery, they were not merely constructing tools, weapons, or monuments. They were sending messages across centuries and millennia that skill and understanding can transcend the limits of time itself. The question remains, are we ready to hear that message? And in seeking out their secrets, might we uncover something far greater than mere precision? Imagine holding a sword whose blade shimmers with a fluid, water-like flow. Beneath that mesmerizing beauty lies a structure so advanced that modern scientists peering through electron microscopes have found arrangements of carbon atoms and iron on a scale so precise it borders on nanotechnology. This is Damascus steel, a material whose very name has become synonymous with both mystery and mastery. Forged in the crucible of ancient knowledge, Damascus steel carried secrets that even the most skilled modern metallurgists struggled to replicate for centuries. But here is the deeper question. Did its creators truly understand the microscopic marvels they were crafting? Or was their genius born of painstaking tradition passed down through generations until the exact process faded into legend? The story begins in the ancient Near East, possibly as far back as 300 BCE. But it was truly between the 9th and 18th centuries that the blades of Damascus, feared by crusaders and coveted by kings, rose to prominence. These blades were made not only to cut, but to endure. They could slice through lesser weapons, hold an edge after countless battles, and resist breaking under stresses that would shatter ordinary steel. What gave them such strength was not magic, though it may have seemed so to the untrained eye, but a complex interplay of chemistry, heat, and time. The core ingredient was Wootz steel, originating from India and Sri Lanka, a high-carbon alloy produced in small sealed crucibles. This was no accident. The sealed environment prevented the loss of carbon during smelting, allowing molten metal to cool into ingots with a distinct microstructure. These ingots were then exported along ancient trade routes to blacksmiths in Syria, Persia, and beyond. There, the transformation into Damascus steel began, a process involving precise temperature control, repeated heating and forging, and an almost ritualistic mastery of timing. This delicate dance determined the alignment of carbon nanotubes and carbide structures within each blade, and this is where the atomic scale intrigue deepens. Modern metallurgical analysis has revealed that authentic Damascus blades contained carbon nanotubes and nanoscale sheets of cementite, arrangements of atoms forming repeating patterns on the scale of mere billionths of a meter. These microscopic structures are not simply aesthetically fascinating. They impart the blade with its extraordinary combination of hardness and flexibility. Achieving such a feat in a pre-industrial world is nothing short of astonishing, comparable to building a cathedral with stones carved to molecular tolerances without ever having seen molecules themselves. Yet this perfection was also fragile. The process was deeply dependent on the unique chemical composition of the original Wootz steel ingots. As trade routes shifted and the original ore sources were exhausted, the precise ratios of carbon and trace elements changed. By the 18th century, blacksmiths found that although their blades retained their beauty, they no longer possessed the legendary strength and resilience. The art, once thriving and guarded, began to fade into myth. However, the allure of Damascus steel never vanished entirely. In the 20th century, metallurgists undertook exhaustive efforts to reverse engineer the process, meticulously combing through historical records, experimenting with crucible smelting techniques, and analyzing surviving artifacts. At the atomic scale, they achieved a measure of success. Modern reproductions could replicate many of the mechanical properties and even mimic the iconic surface patterns. Yet, important questions remain unresolved. Did ancient smiths, through generations of trial and error, stumble upon methods that effectively manipulated matter at the nanoscale without any awareness such a scale even existed? Or was the atomic precision embedded within these blades simply an unintended byproduct of larger, more visible crafting decisions, the careful choice of raw materials, the rhythmic hammering in the forge, the precisely timed cooling cycles, whispered down from master to apprentice like sacred secrets? An additional layer to this mystery arises from the hypothesis that the techniques behind Damascus steel may have roots far older than the medieval Near East. Some researchers suggest the knowledge originated from Hellenistic or even more ancient civilizations, passed down and refined over centuries. If this is true, then Damascus steel may not be a singular invention, but rather the pinnacle of a continuous thread of atomic-level craftsmanship stretching deep into antiquity. This theory aligns with a broader enigma at the heart of our investigation. How many of the so-called miracles of ancient engineering were actually the results of unbroken lines of practical empirical science, now fractured and lost to time? When we compare Damascus steel to other ancient materials, the parallels become striking. Consider Roman concrete, which can self-heal after centuries of immersion in seawater, the nanostructures in medieval stained glass windows, accidentally created by metallic nanoparticles suspended within the glass, or the fused surfaces of ancient South American stonework, hinting at heat or pressure techniques unknown to us. In every case, we witness what appears to be a leap into atomic or molecular mastery achieved without the benefit of a microscope, and often without a formal scientific theory to describe the phenomena. Damascus steel, then, is far more than a chapter in the history of metallurgy. It symbolizes the gap between knowing that something works and understanding why it works. It also reminds us that the boundary between science and craftsmanship is often blurred. To create a blade with the strength and resilience of Damascus steel required not only the physical skill to manipulate metal, but also an intuitive grasp of heat, timing, and the complex behaviors of materials. It was a form of embodied science, where critical data lived in muscle memory and sensory experience rather than in written manuals. Perhaps this is why the loss of Damascus steel's secret still stings deeply. We did not merely lose a manufacturing process, we lost a way of thinking, a mode of engaging with materials that treated them not as inert substances, but as living participants in the forge. This relationship, honed over centuries, produced results that modern industry, with all its precision instruments, still regards with awe. In our journey through ancient machines built with atomic precision, Damascus steel stands both as a triumph and a tragedy. A triumph because it proves that human beings, without electron microscopes or computer modeling, could still shape matter at the smallest scales into tools of unmatched performance. A tragedy because that knowledge slipped away, not through deliberate secrecy, but through the slow erosion of trade resources, shifting cultural priorities, and the fading of tradition. Yet the mystery endures. Each surviving blade lying in museums or hidden in private collections issues a silent challenge to our understanding. If they could achieve such mastery, then what else might they have accomplished? What other atomic arts might be waiting to be rediscovered or perhaps reinvented in our own era? This brings us to the next enigma, one that blurs the line between metallurgy and architecture. If Damascus steel demonstrates atomic precision in the forging of a weapon, what happens when that same mastery is scaled up to monumental proportions, shaping not a blade, but entire structures? If there is one artifact that encapsulates the mystery of ancient atomic-level mastery, it is Damascus steel. For centuries, these blades have been whispered about with reverence, feared on battlefields, and revered in royal courts. They were said to cut through lesser swords like cloth, to shear hair floating in the air, or to slice a silk scarf without fraying a single thread. Their distinctive surface, an intricate flowing pattern that seems almost alive, hinted at something far beyond mere metallurgy. This was not simply a weapon. It was a statement, a mastery over matter itself. Our story begins not in Damascus itself, but somewhere at the crucible of trade linking India, Persia, and the Levant. Historical evidence suggests that the fabled steel was forged from Wootz ingots imported from southern India, a material prized for its purity and unique carbon content. These ingots, themselves an achievement of controlled smelting, were transformed in Damascus and other centers into blades that became the gold standard for edged weapons. But how they did it remains the enduring mystery. When modern scientists first gained access to genuine centuries-old Damascus blades, they expected to find nothing more than simple high-carbon steel. Instead, what they found stunned them. Nanoscale carbon nanotubes and cementite nanowires, so fine and precise they could only be observed under powerful electron microscopes. These are materials associated today with the most advanced nanotechnology, not with forges blazing in medieval marketplaces. How could a smith in the 10th century possibly have manipulated matter at a scale of billionths of a meter? One theory holds that they never consciously saw what they were creating, at least not in the modern scientific sense. Rather, through generations of empirical experimentation, trial and error, and a profound understanding of the behavior of metals under heat and hammer, they developed a process that produced these nanostructures. The natural blend of iron with trace elements like vanadium and tungsten from the ores, combined with an almost ritualistic cycle of heating and cooling, could have aligned carbon atoms into these nanoscale configurations. Their senses were their instruments. Time was their laboratory. Yet there is a counter-theory, one that brushes against the fringes of conventional history. Some researchers argue that these smiths were guided by knowledge that was not merely the result of trial and error, but passed down from an earlier civilization, now lost to time. The precision required to achieve uniform nanowire distribution in steel, is so extreme that even modern metallurgists struggle to replicate it consistently. If medieval smiths had stumbled upon it by chance, why was the method eventually lost? Why did the skill fail to spread, evolve, and dominate metallurgy worldwide? Part of the answer lies in the fragile nature of tacit knowledge. The complex process behind producing true Damascus steel was never recorded in engineering manuals or formal treatises, but was carried within the memories, muscle memory, and practiced instincts of master smiths. When these lines of apprenticeship broke, whether due to war, political upheaval, the disruption of vital trade routes, or societal collapse, the closely guarded secrets vanished with them. By the late 18th century, the true art of Damascus steel had disappeared, replaced by inferior imitations. What is today sold under the name Damascus in markets and shops is often pattern-welded steel, decorative cousins that mimic the aesthetic but lack the otherworldly properties of the originals. Yet, despite the loss, the legacy of Damascus steel forces us to confront some uncomfortable questions about the nature of human history. Could ancient and medieval craftsmen really have had access to principles of atomic and molecular structuring that modern science has only recently begun to rediscover? Was the magic of Damascus steel a mere accident, serendipity born of chance combinations of materials and process? Or was it the echo of a far more sophisticated technological tradition whose origins stretch further back in time than we dare admit? To put this in perspective through the lens of modern materials science, nanostructures are no trivial matter. They are the foundation of advanced electronics, high-performance composites, and cutting-edge medical tools. The creation and manipulation of nanoscale features require highly controlled environments. Clean room laboratories, computer modeling, industrial precision, and extreme care. Yet Damascus blades, forged in smoky forges powered by bellows and anvils, were achieving something similar over 1,000 years ago. Perhaps the most compelling aspect of the Damascus mystery is the intersection of beauty and function. The swirling surface patterns on the blades, often described as watered or flowing, were never merely decorative flourishes. Instead, these were the visible fingerprints of the underlying atomic arrangements within the steel. Each ripple, each subtle wave on the surface, told a story of molecular alignment influenced by careful heat cycles, a dance in which carbon atoms settled into place with remarkable precision over time. Modern metallurgists attempting to recreate Damascus steel often find themselves trapped in a limbo between frustration and awe. Some have come close to reproducing blades with similar nanostructures, but the exact combination of ore composition, trace impurities, forging technique, and cooling rates, the alchemy that gave birth to the original, remains elusive. It is as if the steel itself resists complete rediscovery, guarding its secrets as fiercely as the warriors who once wielded it. The question that lingers unresolved is this: if Damascus steel represents a remnant of ancient atomic precision, then what else might have been possible for those who mastered such crafts? Could they have applied similar nanoscale techniques to tools, armor, or architectural elements? Were these nanostructures merely one facet of a broader, forgotten science? Or was Damascus steel an isolated peak, a singular triumph born from a perfect marriage of nature's resources and human ingenuity? As we proceed, we will shift focus away from the forge and toward the quarries, where stone, rather than steel, bears marks of precision so exact they seem impossible. But keep this in mind: Damascus steel is proof that even without microscopes or the vocabulary of nanometers, our ancestors may have manipulated the very building blocks of matter. And if they could achieve this with fire, hammer, and the wisdom of generations, then what limits truly were there? If the ancients did wield such atomic-level precision, why then did that knowledge vanish? This question gnaws at the edges of our curiosity like an unresolved chord. Lingering without closure throughout history, the march of technology has often appeared as a cumulative ascent, building upon the discoveries of those who came before. Yet, in the cold stone and aged alloys of the past, there exists a strange inversion. Peaks of craftsmanship rising sharply from an otherwise primitive technological landscape, only to disappear and not be reached again until modern times. It is as though the path to progress was interrupted or deliberately rerouted. This paradox is vividly illustrated by the Great Pyramid's alignment, so exact to true north that even modern engineers struggle to replicate it without laser guidance. This precision stands in stark contrast with the archaeological consensus that the tools available to the pyramid builders were simple copper chisels and basic rope plumb lines. The mismatch between means and results is jarring. Were these truly the only tools available? Or have we lost knowledge of a parallel toolkit, one that did not survive in the archaeological record because it was not composed of stone or metal? Ancient precision often appears selective and episodic. A culture might produce one or two pieces of astonishing craftsmanship surrounded by works of visibly lesser quality. It is as if a momentary brilliance emerged, perhaps the flash of a master artisan or a small circle of technologists, only for their knowledge and methods to vanish with their deaths or the collapse of their society. The Antiquity mechanism stands as the quintessential example, a mechanical computer capable of predicting astronomical events with uncanny accuracy. It appears once in the historical record, then disappears for over a millennium. Some argue this is not a mystery, merely the randomness of preservation, that countless other examples of high-precision work once existed, but were lost to time, climate, and human interference. Yet this explanation struggles against the growing weight of anomalies, not just in stonework, but in metallurgy, ceramics, and even textiles, that defy their chronological context and the manufacturing processes we currently attribute to their eras. One intriguing possibility is that ancient cultures possessed what we might call soft technologies, processes, techniques, or instruments that relied less on physical machinery and more on knowledge systems and methods that left little to no durable trace. Think of modern semiconductor manufacturing without the clean rooms, vacuum pumps, or photolithographic masks. At its core, it is a process, an idea. Should a global collapse occur tomorrow, the physical remnants of our most advanced production systems would degrade rapidly, leaving future archaeologists with scant evidence to deduce our true capabilities. Another hypothesis turns to the realm of trade secrets and monopolies. Perhaps there existed ancient guilds, akin to medieval craft guilds, whose value lay in guarding proprietary knowledge, passing it down orally or through tightly controlled apprenticeships. If these guilds perished in war, famine, or political upheaval, their guarded techniques could vanish almost instantly. In this light, ancient precision may have been less about a globally shared skill set and more about isolated pockets of mastery. Yet there is an even more unsettling possibility. Some of this lost precision was the byproduct of forces or tools we no longer possess, and its disappearance may not have been accidental. Imagine a technology so potent, so far ahead of its time, that those in power deemed it too dangerous to leave in circulation. Whether due to fear of misuse, religious decrees, or concerns about societal upheaval, such knowledge might have been deliberately suppressed. The burning of the Library of Alexandria is often invoked here. Though historians debate the scale and timing of the destruction, it serves as a potent symbol of how fragile knowledge can be and how swiftly it can vanish from the human record. Modern reverse engineering efforts reveal just how alien some ancient works appear when subjected to microscopic analysis. The lattice structures in Damascus steel, for instance, were only understood within the last few decades, patterns of carbon nanotubes embedded within iron that give the blade both strength and flexibility. These structures were not intentionally crafted at the nanoscale by medieval blacksmiths, at least as far as records show, yet the consistent results strongly suggest a deliberate, if unspoken, mastery of conditions and materials that today we would recognize as nanoengineering. Similarly, certain Incan stone walls feature interlocking blocks fitted so tightly that not even a razor blade can be slipped between them, all assembled without mortar. Some researchers suspect thermal or chemical treatments, perhaps plant-based acids or unknown binders, were used to soften or fuse the surfaces at the microscopic level before setting into their final rock-solid form. If true, these represent a form of material science that was not only advanced, but deeply practical and yet somehow entirely forgotten.
As we grapple with this paradox, we are forced to confront uncomfortable truths about our own era. We tend to assume that progress is linear and cumulative, but history whispers a different story, one of rises and collapses, knowledge gained and then scattered to the winds. The idea that we might be living in another such peak, vulnerable to the same fate, is sobering. The devices in our pockets, the satellites in orbit, the quantum computers in laboratories, all could become opaque mysteries to a future civilization if the chain of knowledge is broken.
The paradox of lost precision is more than an archaeological curiosity. It is a mirror held up to the fragility of civilization itself. Each impossibly perfect cut, each inexplicable tolerance preserved in stone or metal is both a marvel and a warning. They whisper of what can be achieved, and how easily such achievements can be erased. And as we stand at the cutting edge of our own technological era, perhaps the most important lesson is not simply how the ancients did it, but how we ensure that our own hard-won precision, atomic or otherwise, survives the tides of time. Because if history has taught us anything, it is that perfection is fleeting, and the memory of how to achieve it even more so. The deeper archaeologists peer into the microscopic and atomic details of ancient artifacts, the more the narrative fractures into two seemingly irreconcilable camps. Those who attribute these impossibly precise creations to the ingenuity of human craftsmanship within known historical timelines, and those who believe they hint at lost epochs of technological brilliance, now reduced to scattered ruins and enigmatic relics. By now, the evidence feels like a mosaic with more missing tiles than completed images, tantalizing glimpses of an unspoken chapter of human history. At first glance, the sculptures of ancient Egypt, the tightly fitted masonry of the Andes, or the flawlessly drilled stone beads of the Indus Valley could be explained as mere mastery of hand tools, perhaps aided by simple but clever innovations, but magnify their surfaces to the micron or nanometer scale, and the story changes dramatically. Suddenly, a seam in granite becomes a perfectly planar interface. A polished obsidian mirror reveals a surface so smooth that, by today's standards, it rivals semiconductor wafers. What is striking is not just the level of craftsmanship, but the statistical improbability of such precision occurring repeatedly across cultures separated by oceans, languages, and millennia. This is the point at which some researchers quietly begin to speculate. Were these skills independently rediscovered multiple times throughout human history, or were they inherited fragments from an older global knowledge system? The human timeline, as presented by conventional archaeology, places the rise of complex civilization somewhere around 6,000 years ago, with rapid technological acceleration in recent centuries. But a growing body of physical evidence challenges this neat, linear trajectory. Consider the mysterious Iron Pillar of Delhi, standing tall for more than 1,600 years without significant corrosion. Its surface bears an unusual passive protective film that continues to puzzle modern metallurgists. Or the finely inlaid jewelry from the ancient city of Ur, whose gold-to-silver ratios and micro-soldering techniques reveal a metallurgical sophistication that we typically do not associate with the Bronze Age. One of the most compelling threads in this investigation comes from the realm of ancient metallurgy examined at atomic resolution. Damascus steel, famed for its legendary strength and characteristic wavy patterns, is now known to contain carbon nanotubes, hollow cylindrical molecules of carbon atoms with extraordinary tensile strength, embedded within its steel matrix. These nanotubes are staples of modern nanotechnology, Yet metallurgists analyzing 17th century blades discovered they formed naturally during the forging process. Whether this was an accidental byproduct or an intentional, repeatable technique remains one of the great unanswered questions. If the latter, it implies that blacksmiths in the Middle East were manipulating atomic-scale structures centuries before scanning electron microscopes even existed. Some scholars suggest that artisans observed macroscopic effects, such as the blade's unmatched sharpness or resilience, and refined their methods generation after generation until they could reliably reproduce these results. The process itself may have been a highly guarded secret, its true understanding lost when the last master smiths died. But this leaves a question hanging in the air. Was this merely intuition, honed over centuries, or the vestige of an even older body of material science? Similarly, in South America, one of the most puzzling metallurgical feats involves the mysterious burger alloy, a blend of gold and copper often used for ceremonial objects. In certain cases, the alloying and depletion gilding processes appear to have achieved atomic-scale uniformity, something that even today requires controlled environments and precise thermal management. How these artisans achieved such control without access to modern kilns or temperature gauges remains a mystery that quietly unsettles the tidy boundaries of our historical models. Critics of the lost technology hypothesis argue that extraordinary skill can emerge under the right social and cultural pressures. Civilizations with elite patronage, long apprenticeship systems, and a steady supply of skilled labor could achieve feats that seem miraculous to outsiders. The Egyptian stonemason shaping a diorite vase by hand was no amateur hobbyist. He may have spent decades refining his technique under the watchful eye of master artisans. Similarly, the Incan architect overseeing the fitting of Cyclopean stones may have commanded hundreds of workers in a coordinated, precision-driven workflow where mistakes were unacceptable and materials abundant. Yet, the anomalies stack higher. The more one studies the most extreme examples, the more the statistical likelihood of them being the product of chance and skill alone begins to thin. There comes a tipping point where pattern recognition whispers in the background. This is not just about scattered outliers. It is about systemic mastery across multiple domains, times, and places. Here, the concept of technological punctuations enters the conversation. The idea that human history may not be a slow upward slope, but a series of spikes in technological capability, followed by declines and cultural amnesia. In this model, civilizations might reach sudden peaks of innovation driven by environmental, social, or even outside factors, only to collapse before their knowledge can be widely preserved. The material remnants left behind for future generations are like breadcrumbs from an unknowable banquet. To be clear, these spikes would not necessarily require extraterrestrial intervention or mythical Atlanteans. They could simply be the result of uniquely favorable combinations of resources, cultural priorities, and gifted minds that converge for a few generations before vanishing again. But the magnitude of precision we are discussing, down to atomic-scale craftsmanship, makes the mystery harder to reconcile. The challenge for modern researchers is that most of these relics cannot be reverse-engineered without destroying them. Museums are understandably reluctant to hand over a ceremonial mask or a 2,000-year-old gemstone for metallurgical dissection. As a result, much of the work relies on non-destructive imaging, spectroscopy, and careful surface analysis, leaving the deeper secrets, those embedded in the material's lattice structure, tantalizingly out of reach. This lack of direct access fuels the speculative fire. In its absence, we are left with high-resolution images of nanoscale structures, unexplained consistencies in tolerance and alignment, and the recurring whisper of something older, stranger, and perhaps more advanced than the neat arcs of our history books allow. While the academic mainstream remains cautious, the artifacts themselves, silent, immovable, and stubbornly precise, continue to speak across millennia. In the next part, we will step away from metallurgy and turn to an equally baffling frontier: ancient construction techniques that align megaliths and monuments with astronomical bodies at sub-arc minute precision. alignments so exact that they rival and in some cases surpass modern surveying tools. If the atomic craftsmanship of ancient metallurgy hints at mastery over the smallest building blocks of matter, then these celestial alignments suggest an equally improbable mastery over the vast distances of the heavens. Together, they form a picture that is both exhilarating and deeply unsettling. The deeper we journey into this labyrinth of ancient precision, the more the boundary between possibility and impossibility begins to blur. For centuries, mainstream archaeology has painted a clear arc of human technological evolution, from stone tools to bronze, from iron to steel, from the steam engine to silicon microchips. But when we peer through the lens of artifacts that defy their supposed limitations, cracks appear in that arc. Through those cracks, an unsettling question emerges. What if some of humanity's greatest technological leaps did not happen in the last 200 years, but were rediscoveries of knowledge once possessed and then lost? Consider the quiet revelations coming from modern material science laboratories. Under electron microscopes, certain ancient alloys reveal crystalline alignments so uniform that even with today's computer-controlled equipment, producing such consistency would be prohibitively expensive. Damascus steel, already celebrated for its legendary sharpness and resilience, has been shown to contain carbon nanotubes, tiny cylindrical structures made of carbon atoms arranged in hexagonal lattices with properties so extraordinary that NASA has studied them for aerospace applications. These nanotubes are not incidental impurities. They are integrated into the metal in ways that suggest intentional design. Yet we are told this was simply the happy accident of medieval smiths. If so, why do similar nanostructures appear in other cultures separated by oceans and centuries, in certain South American ceremonial blades, in Japanese katanas of the highest grade, even in fragments of ornamental metal recovered from ancient burial sites in Africa? Patterns begin to emerge, patterns of advanced metallurgy that whisper of a shared, deeper understanding. And if such knowledge existed, what else might have been within reach? This is where archaeology edges into uncomfortable territory. There is a reluctance to admit that ancient builders and smiths could have wielded capabilities on par with, or even exceeding, our own in specific domains. The prevailing model prefers to see history as a staircase, each generation building predictably on the last. The existence of anomalies, especially ones that require explanations invoking atomic-scale precision, threatens to transform that staircase into a far messier landscape of peaks and valleys, lost ages of light and dark. Take, for example, the precise interlocking stones of the Inca walls in Sacsayhuaman. We marvel at their tight joins, so tight that even a razor blade cannot pass between them. Some explanations invoke careful chiseling and iterative fitting, but those who have studied the surfaces up close with modern profilometry note that the stone surfaces aren't just flush. They follow each other's contours with remarkable fidelity over long distances. This kind of precision fitting, even in soft materials, is difficult. Without measurement tools calibrated to thousandths of an inch, in hard and brittle stones like andesite and diorite, it borders on miraculous. Could the shaping process have involved controlled material removal at the microscopic level, perhaps even thermal or chemical treatments that altered the stone's crystalline structure before final shaping? Ancient Egyptian stonework poses similar mysteries. The famous granite sarcophagus inside the Great Pyramid shows signs of flatness and squareness approaching modern machine shop tolerances. Boreholes in granite and basalt exhibit spiral tool marks consistent with feed rates far exceeding hand-cranked drills. Modern machinists have compared these marks to those left by high-speed diamond-tipped boring equipment, technology officially non-existent until the industrial era. If these patterns were isolated, they might be dismissed as coincidences or exaggerations. But when metallurgy, stonework, ceramics, and even ancient optics are combined, the web of anomalies becomes difficult to ignore. In 19th century archaeological digs in Nineveh, Assyrian lenses made of rock crystal were uncovered, some with spherical curvatures accurate enough to magnify images without significant distortion. In the Indus Valley, beads made of carnelian were drilled with holes less than a millimeter wide, perfectly straight and polished smooth. These details aren't merely aesthetically pleasing, they imply control at a scale beyond human vision. This means there must have been measuring tools or feedback systems beyond the naked eye. We tend to view our own era's technology as permanent, as the final and inevitable peak of progress. Yet the archaeological record may be telling us that even mastery at the atomic scale is not immune to the erosion of time. Civilizations can hold the key to manipulating matter with surgical precision and still lose it. When they do, survivors may be left with myths, half-remembered instructions, and artifacts whose makers they can no longer emulate. Imagine if tomorrow every microchip factory on Earth were destroyed, not just the buildings, but the expertise to recreate them within a single generation. The ability to etch silicon at the nanometer scale would fade from living memory within a century. The surviving chips might be seen as magical relics. Within 1,000 years, they could be taken as proof of divine intervention. So when we encounter an ancient gold pendant with filigree finer than a human hair, or a ceramic glaze fused at molecularly uniform thickness, we must ask, are we looking at the pinnacle of that culture's craft, or only what survived, the fragment of a far larger mastery that we have yet to fully match? This is the threshold before our final descent into the heart of the mystery ahead. We will confront the most controversial possibility of all, that ancient precision was not merely the product of lost tools, but the byproduct of an entirely different way of thinking about matter itself, one that might rewrite our understanding of what it means to be a technological civilization. Imagine for a moment that the entire human story is a book, and that we are missing most of its chapters. The pages we hold are worn and incomplete, bound together with fragile strings of surviving records, myths, and ruins. Yet every so often, we stumble upon a detail so sharp, so precise, that it feels as if a sentence from a lost chapter has been etched into the margin, waiting to be deciphered. In the context of ancient machines and atomic precision, these details manifest not just as anomalies, but as echoes, and echoes have a peculiar quality. They carry the shape of the original sound, but with distortions, fading, and interference. The precision artifacts we uncover today may be just such echoes, faded remnants of a technology or knowledge system so far ahead of its time that, even when reduced to ruins, they retain measurable perfection. Take, for instance, the curious case of the Lycurgus cup. To the naked eye, this 1,600-year-old Roman glass goblet is a beautiful piece of craftsmanship adorned with intricate scenes, but under different lighting it changes color, shifting from an opaque green to a deep, translucent red. For centuries, this was seen as a mere artistic flourish. Only modern microscopy revealed the truth. The glass contains nanoparticles of gold and silver dispersed at scales of tens of nanometers, a level of control over material properties that would challenge even modern nanofabrication labs. If such a technique arose in isolation, one might argue it was a fluke, a happy accident of mixing impurities. But that explanation grows shaky when placed alongside other examples. The carbon nanotubes embedded in Damascus steel blades, the crystalline structures in pre-Columbian metalwork, the near-molecular uniformity of certain Mesoamerican obsidian tools. None of these examples were consciously described in atomic terms, yet the results are indistinguishable from deliberate manipulation of matter at that scale. The natural instinct of modern historians is to frame these feats as accidental discoveries, as if the ancients stumbled upon molecular precision without knowing it. But what if their conceptual frameworks, though different from ours, were not blind? What if they perceived patterns, symmetries, and transformations at scales they couldn't directly see, yet could still control through ritualized processes, empirical iteration, and encoded traditions? In other words, they may not have needed to understand why something worked to master how it worked. Consider how long humanity used fire before understanding combustion, or how ancient mariners navigated by stars without knowing stellar distances. Mastery does not always require full theoretical comprehension, only reliable repetition. And in the case of these atomic echoes, repetition might have been bound to systems of craft apprenticeship and perhaps even sacred secrecy. But here lies the tragedy. Precision without preservation is fragile. Once a technique is lost, once the chain of apprenticeship breaks, the method can vanish for centuries or millennia without documentation. In the language of science, future generations might encounter only the artifact, divorced from the knowledge of its making. That is why rediscovering these skills today often comes as a shock. We have no record of the hands, minds, and philosophies that brought them into being. The implications are staggering. If civilizations before us achieved atomic-level craftsmanship, what other sciences might they have touched? Could they have manipulated sound frequencies to alter material structures, engineered composite materials indistinguishable from nature, used principles of resonance, magnetism, or pressure in ways we have yet to replicate? It's tempting to dismiss such speculation as fringe, but remember, only a century ago, the concept of manipulating individual atoms was itself science fiction. Today, scanning tunneling microscopes allow us to arrange atoms like beads on a string. Our disbelief in ancient atomic knowledge says more about the limits of our imagination than the possibilities of the past. There is also a deeper, almost philosophical dimension here. If the universe is, at its core, a dance of particles and forces, then to shape reality is, in a sense, to learn the steps of that dance. Perhaps ancient engineers didn't discover atomic precision so much as they learned to move in time with the underlying rhythms of matter. Ritual, intuition, and craftsmanship could have been the sheet music by which they composed their creations. Some of the most intriguing possibilities emerge when we think of these echoes not as isolated sparks, but as parts of a larger, now lost pattern. The Great Pyramid's alignment, the polygonal masonry of Sacsayhuaman, the finely drilled stone beads of Saqqara, perhaps they were all chapters in a story where understanding structure and resonance at every scale, from the cosmic to the atomic, was the guiding principle. If that's true, then what we're left with are fragments of a lost symphony, notes scattered across time and continents. The question becomes, can we, with modern tools and ancient clues, reconstruct the music? The pursuit is not without peril. There is an alluring danger in projecting too much onto the past, in seeing intentionality where none existed, yet there is an equal danger in underestimating the capacities of those who came before us. To walk between these extremes requires both skepticism and wonder, the very balance that drives science forward. As we stand on the edge of atomic mastery today, capable of crafting quantum dots, manipulating DNA, and building materials atom by atom, we may find ourselves centuries from now in the same position as those ancient artisans. What knowledge will survive us? Which techniques will be rediscovered, causing future generations to ask, how did they do this? It is here, at this intersection of humility and ambition, that we glimpse the true weight of these echoes. They are not just reminders of what has been lost, but challenges, gauntlets thrown across the centuries, daring us to pick them up. And so the question remains, when we finally hold those lost notes in our hands, will we merely marvel at their beauty, or will we learn to play the symphony again? The more we peel back the layers of time, the more it becomes clear that history is not a straight line of progress. It is a jagged path, peaks of brilliance, valleys of loss, where civilizations have risen to dizzying heights of innovation, only for their secrets to vanish into dust, megaliths, metals, and celestial alignments. Each is a whisper from a past that refuses to be silent. And in those whispers lies an uncomfortable truth. Our ancestors may have mastered methods we cannot yet replicate, let alone fully understand. Think of how we speak of the information age as though it is unique. But what if there were precision ages long before us, eras in which the tools of creation reached scales so fine they danced on the edge of the atomic? To us, this sounds like science fiction. Yet in the rusted grains of Damascus steel, in the polished faces of granite blocks, in the fused seams of artifacts thousands of years old, the evidence stubbornly lingers.
If it is not proof, it is at least a challenge to admit that perhaps we have not discovered everything worth knowing.
There is an irony here. Our own technologies, electron microscopes, high-resolution spectroscopy, 3D scanning, have made us aware of this hidden precision. Without them, we would see only old rocks and rusted blades. But now those tools reveal stories. Our textbooks have yet to catch up with stories that rewrite the boundaries between myth and engineering. And so we are left with two possibilities. One, these anomalies are rare accidents of chance, the byproducts of trial, error, and remarkable luck. Or two, they are the deliberate results of lost knowledge, techniques once mundane until the hands that knew them were gone forever. Perhaps there is a third possibility. This is not just about the past. It is a reminder for the future. Civilizations fall, knowledge fades, skills vanish when no longer valued. The question is not whether we can rediscover what they knew, but whether we will protect our own innovations well enough to ensure they survive us. In the end, the mystery of ancient atomic precision is not just a riddle for archaeologists. It is a mirror in which we see both the heights of human ingenuity and the fragility of the thread that connects us to it. And maybe, just maybe, it is also a warning. Thank you for joining us on this extraordinary journey through the universe here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us, where we unravel the darkest mysteries of space.